weird noises. Okay, so next, let's welcome Professor Shuran Song from Columbia University. Professor Shuran Song is also the co-organizer of this workshop, and her research focuses on computer vision and robotics. So I think Shuran said that there might be some network issue on her side, so I would just directly share her pre-recorded video. So Shuran, does that work for you?
Yeah, sounds good. Thank you.
Yeah, okay, thanks.
Mm-hmm. Hello, everyone. Thank you for attending this virtual workshop. I'm Shuran, and today I'm going to talk about our work on learning visual representation for generalizable manipulation. So first, let's talk about what's visual representation and why they're important for robot manipulations. So here I'm showing you a typical pipeline of vision-based robotic system, where the system normally starts with some sort of raw sensory input that try to record the physical world, normally in the form of images or videos. And then the computer vision algorithm will try to convert the raw sensory input into a meaningful representation that describes the environment. And hopefully, this high-level representation can be directly used by the robotic system to perform actions such as grasping the coffee cup or walking around your home. So from this chart, we can see that the representation of the world is really the most critical part of the whole pipeline, because what the representation is determines everything else, from how you're going to process the sensory input to what kind of action you can perform. So for a very long time, the standard visual representation for robot planning was the result of 3D object detection or pose estimation. So this representation has motivated many planning and control algorithms that are designed on top of the food.
Just a quick question: is it really is it kind of silent or smaller sound, or can you guys hear the sound clearly?
Yes, we can hear clearly.
Oh, okay, nice.
Of the object poses. And similarly, it also motivates a big portion of computer vision research in 3D object detection and pose estimation, which also includes many of our own algorithms, such as the approach we used for the Amazon Picking Challenge in year 2017. So the task here is to build a system that's able to pick a variety of objects from a very cluttered bin or shelf and then put them into boxes in order to fulfill online orders. So at that time, we teamed up with MIT MCube Lab to participate in this challenge. So as you can probably imagine, our approach follows the exact classic pipeline, where our group from Princeton is in charge of the vision algorithm that try to infer the object pose from the LGBT image, and the MIT team are in charge of the robot motion planning given the object pose. However, this system does not work as well as we expected. So here are some major issues. So first is about the pose estimation accuracy. So even today, the pose estimation algorithm under heavy cluttered environment is still a very, very challenging computer vision task. And what makes it even worse is that the error produced by the vision algorithm will propagate to the planning system and result in failure execution. So for example, 5 centimeter error in computer vision might be very small, but may directly lead to a collision between the robot and the shelf. And the second issue is about generalization. So because the algorithm heavily relies on the 3D models of the object during training, the algorithm is very hard to generalize to unseen or new objects during testing time. So this approach reflects the limitations of a group of traditional methods that separately consider the perception and motion planning tasks. So in this talk, we'll mostly focus on addressing the second issue, where the goal is to design a generalizable manipulation algorithm where the system is able to directly generalize to unseen objects without the need of a strong prior knowledge about objects, such as their 3D CAD model, predefined categories, and object poses. So in this talk, we'll mostly focus on addressing the second issue, where the goal is to design a generalizable manipulation algorithm where the system is able to directly generalize to unseen objects without the need of a strong prior knowledge about objects, such as their 3D CAD model, predefined categories, and object poses. So to achieve this goal, in the second time when we participate in Amazon picking challenge, we completely change the system to directly predict the action affordance from the camera observation. So for example, the system directly predicts the section point or grasping position directly from the RGBD image without the need of object pose estimation. So this is our final system in action. Because the system that no longer requires object pose information, it can easily generalize to new objects and is able to handle very cluttered environment. So this experience really tells us to think hard about what should be the right visual representation that can better bridge the link between perception and manipulation algorithms in order to make them more flexible and generalizable. So now we have this grasping algorithm. So does it mean that we are able to solve all the grasping problem? Well, unfortunately not. And here are examples of how you can easily break this system. First, since the system relies on calibrated camera and perform open loop execution, the system will not work if you just slightly touch the camera, move the objects around, or raise the table height. And also, since the system can only perform top-down grasp, it will not work if you put the objects on a wall or shelf, which requires a different approaching trajectory. So if we categorize most of the recent work on learning-based grasping, here there's almost none of them is able to really achieve 6-step closed-loop grasping. The reason is that in an open-loop setting, the grasp problem is a lot simpler. Given an image of the environment, the system only needs to predict where and how to pick up individual objects. However, once you start to use the closed-loop formulation, every action the system takes will have effects on the state, which will drastically increase the possible state space the system needs to handle. And if at the same time we move from top-down to 6-step motion, we will also increase the corresponding action space. And together, the large action and state space will make the end-to-end learning extremely difficult. Therefore, to achieve 6-step closed-loop grasping, we really need to address 2 fundamental problems. First is how to get training data or to cover such a large space, and the second is how to design the state and action space to enable efficient learning. Here I'm going to talk about our recent work that's able to address these 2 problems and achieve 6-step closed-loop grasp. So first, let's look at the data problem. Many today's grasping algorithms choose to use self-supervised learning as a way to easily get training data. The problem with this is that this setup only works for simple scenarios where the system can get positive training data by simple trial and error, and it often struggles with more challenging cases. Learning from demonstration is an easy way to solve this problem, but however, it requires an expensive setup and an expert operator that knows how to control a robot, which makes it hard to scale up. So to address this issue, we make this very simple hardware device for collecting grasp demonstration. So this device made of a plastic grabber tool that you can easily buy from Amazon with $20. And we add a wrist mount camera to capture RGBD videos. So this device is designed to mimic the real robot's end effector with a very similar gripper and the same RGBD camera. So this hardware device provides a very low friction interface that enables untrained people to collect grasping data in almost any environment that's no longer limited by the robot's physical access. And because it is a human controlling the gripper, we are able to collect the data for very challenging tasks, such as loading dishes in dishwasher, and without worrying about the robot's failures that may lead to broken dishes, for example. And finally, since the gripper tool is designed to mimic the real-world robot and factor and sensor, the data collected here is much easier to transfer to real robot. So in total, we collect more than 7,000 trajectories, and we can compute the full 6-step pose trajectory of the end effector by using 3D reconstruction. So now we have the data. The next question is how to enable efficient learning from this data. So again, this task is given a current state of the environment represented as an image. We want the system to predict where to move next and eventually lead to a successful grasp. A critical component in this problem formulation is the choice of action representation. Many recent work choose to represent actions using continuous values that hold abstract meaning, such as the end effect offset or joint angles. The issue for this representation is that the mapping between the action and their corresponding effects on the state need to be explicitly learned, or in many cases memorized by the network, which will make the algorithm very hard to generalize to new state and action pairs. Instead, here we use a new action view representation where each action is represented by the prediction of the next state, assuming the system took this action. In this case, the network only needs to look at all the possible next states and find the ones that's most promising in order to execute the corresponding action. So using predictive model for robot control is a common way to improve the learning efficiency. However, the challenge is always about how to obtain an accurate predictive model for all possible actions. So in this work, since the action is represented as a state of motion, and the camera is rigidly mounted on the robot's end effector, we can use a simple view-based rendering as a proxy for the predictive models. So we call this approach action view representation, where the action and its effects on state is explicitly modeled through view rendering. So the system works as follows. As the end effector approaching the target object, the wrist-mount camera continuously gathers a new observation of the environment and aggregate them into a complete 3D scene representation using truncated sign descent function. And then, given a set of possible action to take, we'll use a view-based rendering to simulate the future state with respect to different actions, where each view is rendered as if the robot's end effector moved according to that action. So by evaluating this state using a learned value function, the algorithm is able to select the best action that will maximize the total reward for the grasping success. The system is first pre-trained with human demonstration data and then fine-tuned with the real-world data. This process will continue until the grasp condition is reached and the robot will close its gripper to execute the grasp. So the idea of using view rendering as a predictive model actually can be applied to many other tasks beyond grasping, such as navigation or autonomous driving cars, where the action will directly lead to egocentric camera motion. And of course, the model can also be improved by using more advanced learning-based visual predictive model that considers other properties of the environment. So here I'm going to show you some experiments with our grasping system. We first test our algorithm across different scene configurations, such as tabletop picking, horizontal picking from a vertical wall, and other configurations. Since our grasping formulation operates with full 6 degrees of freedom, the same model works out of the box in all these configurations. And since our algorithm is closed loop, it's also able to handle dynamic environments with moving objects. And here are some numbers and comparisons to other state-of-the-art grasping algorithms. So to quickly summarize, in this project, we show how we can use affordance prediction to achieve generalizable grasping and how to use a new action view representation to enable efficient learning of high degree of freedom closed loop grasping. As we know, grasping is only part of robot manipulation, and there are many more complex tasks, such as object assembly, that require the system to not only pick up the object, but also precisely place the object into its target location. And then in this case, although the system can easily pick up the object from any of these grasping points, without more detailed information about the object, the system will not be able to know how to precisely place the object in order to fit into the target location. This requirement speaks to a general group of tasks that are called kit assembly, where the goal is to precisely place a set of objects into their tight packages in order to form a single unit. And here are a few example kits that's really common in our daily life. So traditional robot assembly system often heavily rely on accurate object pose estimation, which requires objects 3D model and expensive manual tuning for each kit unit. So does it mean that we need to go back to pose estimation pipeline again? Well, the main reason that's why this system cannot be applied in real-world applications is because of their requirements on object pose estimation. Because in many real-world applications, these kits are constantly changing due to promotion or seasonal event, which can happen as often as every 2 months. Therefore, it is not cost-effective to re-engineering the full assembly pipeline in order for every single object. As a result, a large portion of these everyday consumer packages are still manually assembled by human hand. Therefore, the goal of this work is to develop algorithms that can immediately generalize to new objects without the need of accurate object models or their fixed-up poses. So we present an algorithm called Form2Fit, which demonstrates that by learning the general concepts of how things fit together, the algorithm is able to immediately generalize to new objects and kits that's not seen during training. So here are 2 key ideas that enables us to achieve this goal. So first is that we observe that across many assembly tasks, the object's 3D geometry can often provide a strong cue on how they should be interconnected. For example, we can easily figure out which objects goes to which slot by just using their 3D geometry. And to implement this idea, we formulate the kit assembly task as a shape matching problem, where the goal is to learn a dense shape descriptor that directly establishes the correspondence between the object surface and their target placement location from the visual input. And second, we observe that it is possible to acquire a large amount of high-quality shape correspondence data for assembly by allowing the system to automatically disassemble them. It is possible because we know that in many cases, disassemble an object is much easier than assemble them. To implement this idea, we designed a self-supervised data collection pipeline through disassembly. By rewinding the disassembled sequence, we can obtain the ground truth labels for assembly. Here is a video showing the data collection process by using disassembly for different objects. To make the disassembly process easier, we fix the kit to the table to prevent accidental displacement from bad picking attempts. To make the disassembly process easier, we fix the kit on the table in order to prevent accidental displacement from back picking attempts. The core component of Form2Fit is a two-stream matching network that learns to infer geometrical correspondence for the object and their target placement location from visual data. Since these descriptors are orientation sensitive, they allow Form2Fit to infer how to pick and rotate the object before placing it in the target location. Here I'm going to show you the system in action. So first, while the system is trained with objects that has a fixed position and orientation, it is able to generalize to different initial configurations with 90% of success rate. Second, while the system is trained with a single object, disassembly data, it is able to generalize to new scenarios where there are combinations of multiple and different kits. Finally, we test Form2Fit on the novel objects that are not seen during training. So by using the learned shape descriptors, Form2Fit is able to assemble those new objects with over 86% of assembly accuracy. So now we are going to take a closer look on the learned descriptors and see what does the network learn. So here we show the t-SNE embedding of the learned feature representation, where a similar color indicates closer feature distance. So from the visualization, we can see that the descriptors learns to encode rotation information, since the same object with the same orientation will share similar descriptors, and objects with different orientation will have different descriptors. Also, the network learns the spatial correspondence, since the same point on the same object will share similar descriptors. And finally, the network also learns to encode the object identity, since different objects will have very different feature encoding. Here I'm going to show you some of the typical failure case of the system. First, we limited our action space to be top-down only, which means that the system will not work for all assembly tasks. And if we're able to combine this system with the sixth of closed-loop grasping approach we described earlier, then we have the potential to extend this work to support more complex 3D assembly tasks. Second, our system also has trouble handling transparent objects. In some cases, we need to spray paint the object in order to make it visible to the depth camera. So to address this issue, in a parallel project, we try to study how to use machine learning and synthetic data to estimate the 3D geometry of transparent objects. And here is the example results of the system called ClearGrasp. And you can go to the project webpage to find out more details. To summarize today's talk, I have talked about two works that enables generalizable manipulation, one for generalizable grasping and the other for generalizable assembly. In both cases, we consider two important questions. One is about how to choose the right visual representation for given tasks, and the second is how to obtain the training data for learning this visual representation. So to enable the generalizable grasping, we use action affordance to directly map the visual observation to possible grasp actions. And we also use action view representation to enable high degree of freedom closed-loop control. And we train this model with low-cost human demonstration data. To enable generalizable assembly, we study the idea of learning shape correspondence for object assembly. And we train this shape matching function from a self-supervised disassembly data. Finally, I would like to thank all my collaborators and funding agencies, and also thank you for listening.
Yeah, thank you, Shuran, for the nice talk. So, who is the? Oh, sorry, I just do some stuff. Yeah, that's my fault. Sorry. Yeah, thank you, Shuran. So I think, yeah, if you have any questions, please raise your hand. I think we have time for one question. So do you have any questions? Oh, okay. Yes, yeah.
Yeah, sure. Actually, I have a question. So for the closed loop paper, so how do you evaluate the generalization ability of the models in grasping?
Yeah, so I think for that is the typical thing that we do is that we want to test on new objects that is not trained. So that's something that people always do for evaluating generalization ability for grasping algorithms. And we also test on the generalization on different setups. That's something slightly different from the standard like evaluation. So we test on different dynamic environments and different scene configurations like grasping from the wall or like different bins.
Okay, got it. Thanks.
Yeah, and I also see some people asking for the project webpage. I will probably link it in the chat channel afterwards.
Yes, sure. That would be very helpful.
Yeah, thank you, Shuran. So if you guys have any questions, you can also feel free to use the chat. And also, then next let's welcome Professor Yasutaka Furukawa from Simon Fraser University. So just a brief introduction, Yasu has received Outstanding Young CS Research Award, NSF Career Award, Best Student Paper Award at ECCV, and Google Faculty Awards. He's also the co-author for the famous 3D vision paper, Building Rome in a Day. So yeah, welcome.
Thank you. Just checking, can you hear me?
Yeah.
Great, yes. I'm Yasutaka Furukawa from Simon Fraser University. I'd like to first thank the organizers for inviting me to this great workshop with so many other great people. I'm thrilled. When giving a workshop talk, I always mention this, the workshops, the tutorials, the most exciting piece at a conference, beyond the main conference. I'm serious, because I can actually speak with my own free will. I feel like the reviewing procedure actually work sometimes often work as a censorship. I'm so scared of reviewers, I cannot write what I want, unfortunately. Before this is a workshop, so I can actually give a talk with the title CVPR is a Contemporary Art Exhibition. For the workshop title 3D Seeing Understanding, I can do that. And organizer is not going to tell me, oh Yasu, you cannot write this, oh this is wrong, or maybe you can change the title. I don't have to hear that, so I can make this. And this is going to be unusual talk. For first year or second year PhD students, I think this is going to be very interesting. For more senior ones, maybe we just don't talk about these things. For more technical contents, I also said yes to talk another workshop, See Understanding Indoor specifically for ScanNet. So maybe you can check out. I have been specializing in reconstruction for CAD geometry, a CAD model. It's a bit harder to define what is a CAD model, but you probably get the idea. We may call it structured geometry, or I might use the term semantically segmented geometry. The bottom is the movie final clip from the movie Transformer. To really make this happen, our professional modelers have to model the underlying scene geometry with CAD quality, which are effective for model manipulation, editing, effect mapping, physics simulation, the interaction, etc. And of course, not at this level. I have been working on making this kind of a CAD-like model from raw image sensor data, from ground level to aerial, indoor, outdoor. So here is a list of papers at the top tier conferences, so should be a good success. But now I want to have a high standard to rate these papers based on the impact to the real world. So here is my rating at the right. This is the actual paper has a real impact to the world, production ready or maybe in production. At the left is the extreme where you see an anger red face icon. This is the anger of engineer. We implemented our algorithm, found out it's not really working, useless. So that's showing the anger of the engineer. So as a first year, second year student to computer vision, you may be shocked. Oh, all our research is actually useless, no impact. All the people talk about impact is the most important. Or senior ones may think, oh, research shouldn't be for real production. So everything should not be production ready. Both are good views. About a week ago, Aaron Hertzman posted an essay on contemporary art. He is a famous computer graphics, vision, machine learning researcher. This is an essay on the contemporary art with some reference to our computer graphics vision community. And what I found interesting is a post, comment by Alyosha Efros. You can read here, but focusing on this, 90% of CVPR papers will turn out to be junk, either immediately or after a few years, which I actually agree. So is 90% of contemporary art. This is not the main message of the essay, but if you read the essay, by the way, Aaron always write amazing essay article, you should read it. Our research is similar to contemporary art. So if I'm going to add 3 words here, this implies CVPR is a contemporary art exhibition. Most stuffs are garbages. If you really find 1 or 2 pieces that speak to you, it's a great success. And there even exists a law, Spurgeon's law, 90% of everything is a crap. And so this conversation of top researchers, which everybody respects, maybe if I interpret, CVPR is a contemporary art exhibition. Most ideas actually garbage. So let's stop pretending that all our papers convey good ideas. Let's stop confusing engineers or fellow researchers because they're actually bad ideas, not great. And again, for the junior ones, this may be actually a little bit disappointing. Research is actually bad, useless often, but not really. My message is the bottom one. The garbage ideas lead to impact. I want to convey this idea in today's my talk. So let's get back to this. So again, right, the real impact. Left, far from impact. But I was more judging as a system as a whole, how useful this is. There are actually many shining pieces, ideas in each paper, and these ideas influence my other paper. So for example, hope you see my mouse cursor. So these two ideas, although system by itself are not ready, but these ideas, some pieces contribute to another paper with a real impact. Or another paper like this, I feel this is a great idea, say this year's paper, CVPR, but we don't see an impact yet, maybe in a few years, or maybe not. By that time, this may become a garbage, but has a potential. Or idea which I thought is cool, extended it, but realized it's a bad idea, so we stopped exploring. So there's idea flow, which have some influence to the impact later. So if you think of what are garbages, maybe now I have less garbage. So these ones do not have an outgoing edge to the impact. So these are garbages, but I have more good stuff. These papers were worth being published for the sake of the world. But now let's look at the top left paper. This is the Manhattan World Stereo paper with Brian, Steve, and Rick. Fairly well cited, nearly 400 citations. If I'm saying that this paper with pretty decent citation is actually a crap because there's no way to impact. Maybe again, many of you may be disappointed. Oh, research is bad. Well, not really, because I'm not adding the inverse arrow. So this is the arrow of the inverse effects, or maybe lessons learned. This paper has a bad idea, so we shouldn't do this. Let's do the opposite, or maybe the other way. So this paper has a role to lead us to the right direction by giving you a bad idea. So this paper has many bad inverse arrows, but eventually lead to impact. So given these arrows, the Manhattan World of Stereo has a way to impact like this. So it has a meaning. So sometimes, of course, ideas come from others. Many ideas by reading other papers from other fields. Actually, many more arrows should be here, but to be simple, let's just pick one. We borrow idea from recognition community to reconstruction here. Well, sometimes shining piece, great idea comes out of nowhere apparently. So my student Chen Liu, one idea come out of nowhere. Maybe he has some inspiration source, but I don't kind of see what was. So great idea comes out of nowhere without using other previous ideas. This kind of thing happens. So now given this, if you think about all the garbages, maybe I have only 3 garbages. So all these 3 have no path to the impact, but maybe once I have this arrow working, so our CVPR paper this year has an impact, this is going to be also the impact, meaning non-garbage. So now I want to talk a bit more technical content. What are the lessons I learned? What are the important things you have to know in doing structured geometric reconstruction? So when we do around research around this, this was the lessons I learned. Top-down procedure is better than bottom-up. If you detect primitives, you want to detect higher level primitives as much as possible. And this is the meaning. Let's say we want to reconstruct a floor plan from a 3D scan. So you go to a house, say 3D smartphone, like a Google Project Tango, or use Matterport style 3D scanner. Get 3D points, look up from the top, then recover floor plan. Bottom-up procedure is you first use lowest level primitives, corners. Use convenet, you can do corner direction. You may get some false positives here and here. You get some corners. And now you find connections, pairs of corners to find edges. Then also you find a set of edges to form rooms. And that's how you go from zero-dimensional corner, one-dimensional edge, to two-dimensional region, room. That's the bottom up. The problem is that once you miss one true positive primitive, say miss a corner, you're going to automatically miss incident edges and incident room. So typical recipe for not recipe, typical fatal bottom-up procedure is you cannot miss a single primitive in the enumeration procedure. You enumerate much more than necessary, but the number of primitives, the space, enumerate grow exponentially as the degree of freedom of the primitive grows. So corner has 2 parameters, edge has 4, room has a lot more. So this becomes more and more difficult and typically fall apart if you really go for higher level geometric structure. On the other hand, if you do top-down, you're first trying to detect high-level primitives, say region, in indoor case a room. And if you want to say there's a room here, it's okay to not seeing a corner here or here. Maybe one may be totally obscure due to, say, occlusion to clutter in the scanning procedure. You can robustly say there's a room by collecting all the information. So hopefully this is intuitive. Room detection is much more robust than corner detection. And once you find these rooms, do some procedure to find the one-dimensional edges or zero-dimensional primitives. It's not easy actually how to go from region to this, but if you know how to, it's much better than bottom-up. So that was a lesson I learned. So for this paper, if you look at the conclusion of the paper, this is what we wrote. But maybe I should have written the following way. So by the way, this paper has many other great contributions. This paper won the Best Student Paper Award by ECCD, so that's a great stuff. But for the technical content, I should have written in the bottom-up procedure, successful primitive generation enumeration is exponentially more difficult. Do not believe that the bottom-up algorithm will be robust enough for production. The community should explore top-down, blah, blah, blah. I should have written. But if we wrote that, likely the paper may not be accepted or may not even win an award. Or actually, I didn't realize this fact back then. Now I feel that way. But this is a real conclusion we should put for the paper. Now, starting from this, we realize, yes, top-down is great. So let's use top-down to do some research here, which unfortunately don't have an orange outgoing arrow. So shape grammar is our great invention from the graphics community. It defines a set of rules defining how, say, residential houses are formed. Say the first rule takes an empty land, then picks a foundation type, say from consisting of 1 rectangle, 2 rectangle, 3, or L-shaped or U-shaped. And after that, you define a roof type for each foundation, etc. So you're going to apply a sequence of rules to make a house. For reconstruction, you're going to sequentially solve a classification problem to pick a branch, and also solving a regression problem to estimate geometric parameters. That's how reconstruction happens. Pretty actually unique and interesting. And we get nice looking demos and interesting house models, which look impressive. The problem is that the grammar is not really general enough, flexible enough to capture many real buildings. We ignore the 40% of the buildings we wrote at the complex class in the paper. We removed 40% of the examples because the grammar couldn't explain. And these are data from UK, England. We actually avoided touching London or major city centers. So those buildings actually much more complicated, which grammar can't really represent, or we cannot find a good grammar. So as you go to the right, it becomes more and more complicated. It's just so difficult to find a proper grammar. That really becomes the bottleneck. When we wrote a paper, the top, that was our mindset. We want to use a shape grammar to help reconstruction. This is a very strong domain knowledge. And we made shape grammar manually, but there's another field called inverse procedural modeling, which takes examples, then derive a grammar. In my view, the IPM, this field is also struggling for a long time without the real impact. It's a very hard problem. So this actually isn't going to work well. Bad idea, I think, because manual design can handle very complex buildings. And IPM isn't really working well. So the potentially good idea is maybe we solve inverse procedure modeling and procedure reconstruction all together in one step. Just consuming a bunch of examples, learn the types of buildings, patterns of buildings automatically, implicitly, with big data machine learning techniques. Then maybe do some reconstruction. So this has some lessons. Bad, maybe another one. And this one out of nowhere, DNN enables use of powerful optimization instead of replacing optimization. So let's pick the outdoor architecture reconstruction vectorization. So take Google Maps image, then make this kind of a planar graph. What the paper proposed was essentially the procedure of detecting these primitives, corners, edges, or regions, and then use some optimization procedure to solve the final planar graph. If you are new to vision, you may not know how we solve vision problems before deep learning comes in. Almost always use the graphical model inference or MLF for pixel labeling. So MLF is amazing. It can handle millions of variables because you have to label million pixels in image. But the inference power is actually very weak. It can only handle pairwise potentials, and potentials have to be usually mostly submodular. Any hard energy just doesn't converge well. And on the other hand, integer programming, this is very powerful, but doesn't scale to many variables. So what really DNN enabled us is to use IP. By shrinking the problem size, we can cut out the impossible solution or unlikely solution by DNN, and also derive some energy term in the optimization, which are kind of nearly convex and easy to optimize. So DNN allows us to use a powerful IP optimization technique because IP can solve for complex topological inference, but DNN is not really good at that kind of that problem. So that was a message we learned. And the other one, this one, this is the instance segmentation from the recognition community. Usually instance segmentation is used for semantic rich instances, say human, cow, bicycle, house. If you see it, you know this is human. For reconstruction, our instances are one wall, another wall. Everything is a wall, no texture. It turns out that you can just replace our training data, and these techniques works for geometric instances, basically plane or wall. And that's kind of, we got that idea from the recognition community. And this one, our paper this year has 2 lessons learned arrow. We learned that the grammar is very bad to use explicitly. So why not implicitly extract the grammar or use grammar-like information? Although I said optimization is great, make things really work, a production, very actually complicated. It's a nightmare for engineers, not great. So we are trying to simplify remove optimization, trying to do some high-level topological inference by data-driven techniques to be more robust. Here's another trial we are doing now. So this is the research flow. And ideally, I hope that all these papers we do have outgoing arrows to other researchers, other papers. Probably not bad, all the arrows are red. So people know our group does always bad ideas. So let's read their papers with the opposite. Totally fine. That's the way to make a contribution to the impact. Maybe the worst is no arrow at all. People don't read your paper. Maybe that's the worst. So to summarize, CVPR is a contemporary art exhibition. Most ideas are garbages, will be garbages soon. But garbage idea leads to impact. So don't be ashamed of your garbage ideas. Don't confuse fellow researchers and engineers by pretending your papers are great ideas. CVPR is starting now, so hope you're going to find your masterpiece at CVPR. I'd like to thank my supervisors, colleagues, student postdocs, whose inspiration really allowed me to form my research idea flow. Thank you very much.
Yeah, thank you, Yasu, for the nice talk. So if you have any questions to Yasu, please raise your hand, and then yeah, and then we can discuss this in live. Do you have any questions right now? Okay, see ya.
It's unusual talk, so I'm not surprised.
Yeah.
Hi, Yasu. So for that paper of CVPR 2020, so how do you do the implicit like grammar learning like in their work?
Yes.
Can you briefly introduce a little bit?
Yes. So maybe grammar is a bit overstatement. We simply take all the examples. Then let's see. Well, it's a bit hard to explain, but in short, the last higher level topological inference. So what are the typical edge connections? That's what we actually learn. Sorry, I'm not answering pretty well. Maybe you should read the paper, but it simply take the models, the raw sensor data, produce a model. Along the procedure, they learn what are the typical junction shapes or typical arrangement of corners. That's actually one step. And we are exploring another idea. It's really sort of inverse procedure modeling and procedure reconstruction together. This is actually one minor step.
And you propose a very interesting idea that the CVPR is a contemporary art exhibitions and most of our papers are garbage. So in your perspective, do you suggest us to create more garbages or to make some like masterpiece, like at least in our mind?
Great question. I think the fact is when we start a project, we always have a goodwill. This is going to be a cool idea. And I think I'm really trying to have a high standard. When the project is over, maybe half of the time, it's a great idea. I'm more like confident. After a few years, I realized actually these are bad. So really like maybe 20% survive. And maybe half of the paper I'm gonna write, I know this is a bad idea. But I have to pretend the great ideas for the sake of publishing. Maybe for minor cases, improve numbers, but the overall too complicated for anyone to reproduce or use for real production. So kind of complexity is something we do not really evaluate for paper, but engineers care about. So just make it too over complex and not really good for the real use.
Yeah, that's true. Thank you for answering my questions.
Yeah, thank you all. So if you have more questions, please feel free to use the chat room. And yeah, so if you have time, you may also look into the chat room to see if they have any further questions. Yeah, okay.
Thank you.
Yeah, thank you guys. So I think next is our, again, the oral session. And we'll have 3 invited papers and each will have 10 minutes. I'll just show their videos and also feel free to use the chat room to have any questions. Yeah. Okay.
Hi, I am Mohammed, a PhD student in Max Planck Institute for Intelligent Systems. Today I will present our CVPR paper Vibe, Video Inference for Human Body Pose and Shape Estimation. This is a collaboration between Nikos, Michael, and me. Human motion is interesting and creative in many different ways. This motion can express the goal and intention of a human. Maybe this is why immediately after the cameras, people came up with creative ways to record human motion. And more recently, with the emergence of computers, researchers try to capture and track human motion in 3D. So why do we do this? Well, modeling human motion hardly needs any motivation. It finds extensive use in AR/VR applications, where you need virtual humans, interaction with intelligent systems like robots,
Is the audio gone?
Shuran, I think we can hear the voice right now.
Okay. So can you guys?
I can hear your talk, but not the sound from the video.
Okay, yeah, let me check.
Audio from the video.
And cannot even capture the most obvious objects.
So can you guys hear it now?
Yeah, maybe you can start from like study.
Okay, yeah, starting.
Unfortunately, this state-of-the-art Mascar CNN cannot even capture the most obvious objects. Motivated by these applications, our goal in this paper is to estimate human body pose and shape from a video. Here we tackle the problem of predicting a body model representation for each frame of a video containing a single person. We use the simple body model as the representation. Simple is a generative model that factors human bodies into shape, how individuals vary in height, weight, and body proportions, and pose, how the 3D surface deforms with articulation. Simple is a differentiable function that outputs a triangulated mesh. It also provides 3D key points, which are useful for human pose estimation methods. A common approach to estimate simple from images is an end-to-end framework called HMR, Human Mesh Recovery. So HMR passes an input image I through a convolutional encoder. Convolutional features of the image are sent to a regression module whose objective is to infer the 3D human body and the camera. Then 3D joints are projected to 2D using the estimated weak perspective camera. A reprojection loss is minimized to match projected and ground truth 2D key points. The reprojection loss encourages the network to produce 3D bodies that explain the 2D joint locations. However, implausible 3D bodies or bodies with gross self-intersections may still minimize the reprojection loss. To regularize this, they use a discriminator network that is trained to tell whether simple parameters correspond to a real body or not. Real body samples come from a large collection of simple bodies registered to real human scans. In a recent extension called Temporal HMR, they extended HMR to work on videos. Temporal information helps to improve their results. However, it fails to produce accurate predictions as shown in this video. A major reason behind this is the lack of in-the-wild ground truth 3D annotations, which are not trivial to obtain even for single images. Therefore, they combine indoor 3D datasets with videos having 2D key point annotations. However, these datasets have several limitations. Firstly, indoor 3D datasets are limited in the number of subjects, range of motions, and image complexity. Secondly, the amount of videos labeled with ground truth 2D pose is still insufficient to train deep networks. Thirdly, pseudo-ground 2D labels are not reliable for modeling 3D human motion. To address all these problems, we take inspiration from HMR, that uses an adversarial training approach. However, we want to be able to train a temporal model. Then the question is how to obtain realistic motion sequences in sufficient quality for adversarial training. For that, we leverage the large-scale 3D motion capture dataset called AMAS, which is sufficiently rich to learn a model of how people move. Our approach learns to estimate sequences such that a discriminator cannot tell the difference between the estimated and AMAS motions. We call the resulting method VIBE. Here, given the video of a person, we train a temporal model to predict the simple parameters, while a motion discriminator tries to distinguish between real and predicted sequences. Everything is trained end-to-end in a conditional generative adversarial manner. Let's dive into the details of our approach. Given an input video of a single person, we extract the features of each frame using a pre-trained CNN. This CNN model comes from a state-of-the-art human mesh recovery model called SPIN. Convolutional features are processed using gated recurrent units, which is a type of recurrent neural networks. GRUs help to incorporate temporal information flow. Then the parameters of the simple body model are estimated for each time step. We refer to the model described so far as the temporal generator. The intuition behind this model is that future frames can benefit from past video pose information. This is especially useful when the pose of a person is ambiguous or the body is partially occluded in a given frame. Assuming that the temporal generator produces pose predictions lacking realism, we use AMAS as the source of real motion sequences, so that we can train a motion discriminator that can differentiate fake and real examples. The architecture of motion discriminator is fairly simple. It has a multi-layer GRU model that takes a sequence of poses as input, followed by a self-attention layer, and a linear layer that predicts a binary classification label. Here we use a self-attention mechanism instead of using the final hidden state or some handcrafted combination of intermediate hidden states. The reason is to be able to amplify the contribution of the most important frames in the final decision. Overall wipe loss is composed of 2D key projection loss, 3D joint loss, simple pose and shape losses, and the motion discriminator loss. Note that 3D losses are applied when 3D annotations are available. To train our method, we use a mixture of 2D and 3D datasets, similar to previous work. Here I will present some quantitative results. For the evaluation, an in-the-wild benchmark called 3DPW is used. We report the mean per joint position error. It measures the Euclidean distance between predicted and ground truth joints. This bar chart shows the joint error on the y-axis and different methods on the x-axis. Lower error means better performance. Here, HMR and SPIN are frame-based pose and shape estimation methods. On the other hand, temporal HMR, THMR in short, and Vibe take video as input. Vibe improves the performance of previous state-of-the-art method by 20 mm. This chart shows the performance of models with and without motion discriminator. We observe that using a motion discriminator improves the accuracy. Let's see some qualitative results from Vibe. This sequence shows some diverse range of motions from a soccer game. Note that Vibe can perform well in the case of motion blur too. We obtain multi-person results using a real-time multi-object tracker. Therefore, inference happens in real time if the number of subjects is less than 5. In summary, we present a state-of-the-art video pose and shape estimation method. We show that discriminative training of motion sequences using the AMAS dataset contributes to better performance. Before concluding my talk, I would like to show a failure case on the video that I displayed at the beginning of my presentation. Obviously, this is what happens when you don't take scene constraints into consideration. Thanks for listening. You can find more about our project from the links on the slide.
Yeah, thank you for the talk. And if you have any questions, please feel free to use the chat room to chat with the authors or share your suggestions, share your ideas. So next is the second paper.
Hello, my name is Danny Dries, and today I would like to talk about our recent paper, Deep Visual Reasoning, which is the idea of predicting an action sequence for task and motion planning from an image of the initial scene, such that ideally only a single motion planning problem has to be solved. Consider the following scenario where the goal is to place the yellow box on the red spot, which is occupied by the blue box. There are other objects present in the scene and the robot arms have to collaborate to solve the task. Such sequential manipulation problems are challenging since they inherently involve continuous and discrete aspects. Task and motion planning approaches address this by combining reasoning on a symbolic logical level with continuous motion planning, such as nonlinear trajectory optimization or sampling-based methods like RRTs. The symbolic level, commonly defined in terms of first-order logic, proposes high-level discrete action sequences for which the motion planner tries to find motions that either fulfill the requirements induced by the high-level action sequence or return that the sequence is infeasible. In this scenario shown here, there are about 500,000 discrete action sequences up to length 6 that reach the symbolic goal. At the same time, due to kinematic constraints such as reachability or joint limits and other objects that act as obstacles, the majority of the discrete action sequences are infeasible and therefore, many motion planning problems have to be solved to find a feasible solution. To overcome this combinatorial complexity, the main idea of this work is, given the scene and the goal as input, to learn to predict promising action sequences such that ideally only one nonlinear program would have to be solved to find a solution to the overall problem. More specifically, we propose a deep convolutional recurrent neural network that predicts action sequences for task and motion planning from an initial scene image. So basically, by looking at the scene, the network will predict the action sequence. We develop how this network can be integrated into the tree search of logic geometric programming. And the cool thing is that although the network has been trained on only 2 objects in the scene at the same time, it generalizes to scenes with multiple objects. A key aspect why this is possible is because we represent the scene and the goal in the image space. First, I will quickly summarize logic geometric programming, or LGP, which is an optimization-based approach to task and motion planning. The idea is, given a scene S, to find a path X in the configuration space of all robots and objects as the solution of an optimization problem. This path consists of k faces with length t. The number of faces is part of the decision problem as well. And now the important part, the costs and constraints are parameterized by a symbolic state variable s, and the time discrete decisions between this state are subject to a first-order logic language through action A, which are grounded action operators. The goal is specified symbolically by G. Then an LGP looks like that. The key difference to a normal trajectory optimization problem is that the discrete aspects of the manipulation problem are incorporated into the costs and constraints through the symbolic state S, like in a mixed integer program. But since this state variable S comes from a logic domain, it introduces more structure to the problem. The logic defines a decision tree where each node represents a nonlinear program. Solving an LGP means a tree search over a sequence of actions such that one reaches a leaf node of that decision tree and the corresponding nonlinear trajectory optimization problem is feasible. So far, LGP relied on lower bounds, which are simplified trajectory optimization problems to guide the search. However, if we remember the scene from the beginning, there are about 500,000 leaf nodes here. And the problem is that many actions in early phases of the sequence are feasible, therefore the lower bounds do not help much. To overcome this, if we could learn, given the scene and the goal as input, to reason about promising action sequences before checking them, the number of nonlinear programs that have to be solved could greatly be reduced. However, one of the big questions here is how the objects in the scene and their properties as well as the goal can be represented as input to the learning algorithm in a way that not only allows generalization over different object properties, but especially also generalizes over changing numbers of objects in the scene. Let us first define for the scene S and the goal G the set T as the set of all action sequences that reach a symbolic goal, hence candidates for a feasible solution or leaf nodes of the tree. With f of a1 to k, we denote the feasibility of the action sequence a1 to k. The first idea might be to collect data and then learn a function f hat that approximates this feasibility function f. However, querying this f hat over all possible action sequences and choosing the one where f hat has the highest value is intractable due to the size of t. Instead, we want to learn a function pi that decides whether an action ak at step k of the sequence is promising in the sense of there exist future actions up to capital K, which not only reach the symbolic goal, but the corresponding trajectory optimization problem is also feasible. All that conditioned on the goal G, the scene S, and the actions taken before. During the tree search, one would then follow at each step the action where pi has the highest prediction. It turns out that through a data transformation, learning pi can be framed as as a well-defined supervised learning problem, which I state here, but I have to skip details due to time constraints. One might ask what the difference of pi is to a goal-conditioned universal Q function. It is very important to understand that in LGP there is no clear notion of state. The symbolic state S neither contains all relevant geometric information nor takes into account the effects of the previous or future actions. To explain what I mean with that, look at this here, where each arm should grasp a box. Now, if in the future an additional action is taken, namely to place the blue box where the yellow one has been, it influences the trajectory of the past. While this is one of the major strengths of LGP, allowing it to solve impressive problems, it makes learning much harder since there is no clear notion of an intermediate state as required in Q functions. Now the big question we have not talked about yet is how the actions, the goal and the scene can be input to the learning algorithm in a way that allows generalization over multiple objects. Fixed-sized feature vectors are problematic in this respect. Given an action A, we decompose it into A bar and O, where A bar is the discrete action operator symbol, for example grasp or place, and O is the tuple of object the action operates on, for example box and table, if the action is to place a box on the table. The goal is similarly decomposed. We now can input A bar and G bar as a one-hot encoding into the network since the cardinality stays the same, independent from the scene. The key is to encode the object tuples O in an image. This image consists of masks indicating which objects are involved in the action, as well as a depth channel that shows the relation to other objects. This is the key to both good performance and generalization to multiple objects, while the input size of an image stays the same, no matter how many objects are in the image. The network we propose consists of CNNs that encode the action object images and the goal image, as well as fully connected layers that encode the action operator symbols and the goal symbol. The resulting encoding vectors then fit into a recurrent module, which takes care of sequence prediction. Since the robot has only access to the initial scene image, this recurrent part implicitly has to learn the effects of the actions on the environment without explicitly being trained on, for example, to predict a future state, which is, as explained before, not really well defined. Now to the experiments. Due to reachability constraints, the two arms have to collaborate. Here the network proposes a handoff solution and the first predicted action sequence is feasible. Handover solutions are only possible if the object is large enough. Since here the green box is too small for a handover, the network correctly proposes a different solution. During training, only two objects are present at the time. The cool thing is now that the network generalizes to scenes with multiple objects. Here we can see an interesting and efficient utilization of the two arms the network proposed to solve the task. It also knows when a single arm is enough, or can solve more complex problems with long action sequences in the presence of multiple objects. We also performed real robot experiments. One has to state here that we still need a perception pipeline to get the shapes of the boxes for the trajectory optimization, which also allowed us to use rendered images, such that we could use the network we have trained in simulation. Also here the network reasons about the geometry of the scene and directly predicts the action sequence required to solve the task, such that no search was necessary. Here it will do a handover. By the way, the ability of the system to perform handovers evolves from the parameterization of the trajectory optimization problem and is never explicitly represented. I kind of find the handover solutions interesting. Let's look at some plots. The plot on the left shows the total solution time over the length of the action sequence. Even for sequence length 6, the median is only 2.3 seconds with an upper whisker of 7 seconds. The plot on the right shows the number of nonlinear programs that have to be solved. As one can see, most of the time the first proposed action sequence is actually feasible. This means that search can basically be eliminated, since the network knows by looking at the scene which action sequence to choose. For sequence length 1 and 2, the network has 100% accuracy, but also for sequence length 6, with a median of only 2 NLPs that have to be solved. This is really cool, I think. If we compare that to LGP tree search, here shown on the right, one can see that this problem is actually hard for LGP with solution times going into the thousands. For sequence length 4, with our network, it is 46 times faster, 100 times for length 5, and for length 6, even 700 times faster in median. Now this plot shows the total solution time over the number of objects in the scene. As a reminder, during training, only and exactly 2 objects are in the scene. Although the network inevitably makes some mistakes, the solution time barely increases for more objects, which I think is really cool. To conclude, we have proposed a deep neural network that predicts promising action sequences for tasks in motion planning from an initial scene image. Most of the time, the first predicted sequence is feasible. Although being trained on only 2 objects present in the scene, the network generalizes to multiple objects. An important assumption and therefore limitation of this work is that the initial scene image has to contain all relevant information, which means that there should be no total occlusions or other ambiguities. If you're interested in more details, check out the full paper, which just got accepted for RSS this year. Thank you.
Yeah, thank you for the presentation. So for the next one, I think Shuran will help present their newly recorded result.
Sure. Okay, see the screen right now?
Representation of scenes for actionable spatial perception. In many applications, such as mixed, augmented reality, or autonomous driving, it is important to have a 3D map of the environment that ideally goes beyond the geometry of the scene by semantically labeling the objects. This is important for high-level understanding, such as in safety-critical applications like self-driving cars, where you want to avoid pedestrians or other cars. Ultimately, we want robots to be able to navigate in indoor environments, potentially interacting with humans. Therefore, there is a need to develop simultaneous localization and mapping algorithms, also known as SLAM, that go beyond accurately estimating the location of the robot and the map of the scene, but that also semantically label the scene. Therefore, previous to this work, we tackled the problem of 3D scene understanding by developing and open sourcing a real-time metric semantic SLAM pipeline that we named Chimera, which is able to reconstruct the 3D geometry while semantically annotating the scene by using visual and inertial data, everything while operating in real time. Here I'm showing a top-down view of a large-scale scene reconstructed by Chimera. I will not have time to present Chimera itself, but let me refer you to our paper for details on how Chimera works. In this talk, I will focus instead on how we turn the raw 3D metric semantic mesh into an actionable 3D representation. In particular, we want our new representation to solve a set of problems, or at least to make them easier to solve. First, we want our representation to allow for path planning queries that are semantically meaningful, such as commanding a robot to go to the kitchen. Such command not only requires to know where the kitchen is, but also, if the scene is very large, it requires an abstraction, such as a topological map, to be able to plan efficiently a collision-free path to that room. Moreover, since as humans we prefer to reason in terms of higher-level abstractions, our map needs to encode higher-level concepts such as rooms and buildings instead of just objects. Finally, we would also like to encode dynamic agents in the scene, such as humans. To achieve these requirements, we propose a 3D dynamic scene graph, or DSG. A DSG is a tree-like representation that abstracts a dense 3D model, such as a metric semantic mesh, into higher-level spatial concepts. For example, objects and agents in layer 2, places and structures in layer 3, rooms as in layer 4, or even buildings in layer 5. This representation is compact, modular, scalable, fast to build, and most importantly, actionable, as we will see next. Our approach is inspired from the work of Armeni colleagues who presented last year a semi-automatic way to build a similar hierarchical representation, which was focused instead on static scenes. Our representation further allows for actionable queries, such as semantic path planning. It maps as well dynamic agents, and it is built fully automatically. In this work, we use a photorealistic simulator to test our approach. On the top right, you can see a rendered image of the scene. And we also simulated humans in an office space, thereby allowing for dynamic entities, which creates several challenges that we explain later. And we also have objects in the scene that we try to detect, reconstruct, and encode in our DSG. So let's start by describing layer by layer what a DSG encodes. As the first layer layer of our DSG, we have our 3D metric semantic mesh reconstructed by Chimera. In layer 2, we model objects by their 3D centroid, a bounding box, its semantic label, and its instance ID. To extract objects from the semantically labeled 3D mesh, we first extract all 3D meshes that have a given semantic label, such as a chair. Then, using Euclidean clustering over the 3D meshes, we segment the objects into multiple instances. Once we have the instances, we can compute its centroid and its bounding box. We distinguish between two types of objects: known, for which we have a 3D CAD model in our database, and unknown, which has no prior 3D model. For the known objects, we fit its model by first extracting 3D key points between the estimated 3D mesh and the CAD model 3D mesh. We then match all 3D key points between the source and target models. Of course, this will introduce a significant amount of outlier correspondences, but by using outlier robust 3D registration techniques that we recently developed, we can faithfully register the 3D models. Still in layer 2, we also model dynamic agents, such as humans, robots, and so on. For each agent in the scene, we build a 3D pose graph, a 3D mesh model describing their potentially non-rigid shape over time, and a semantic label. Having dynamic objects in the scene complicates significantly the state estimation of the robot and the mapping. Therefore, we make use of the semantic and inertial information to counter its effects, as we will see later. Let's first see how the human agents are detected and then tracked. We first detect a human by extracting a bounding box in the RGB image using the semantic segmentation. Then we use a graph neural network from Professor Danielides' group that infers an approximate 3D mesh model. And while this approach works fairly well given an approximately clean 2D bounding box of the human, it sometimes returns wrong estimates that we must deal with when tracking humans. For tracking, we build a pose graph with a motion model, such as zero velocity model, for example, where we incrementally add a new vertex upon a new human detection. We further avoid the potential outliers from the detection module and also solve the data association problem by looking at consistency between joints, which accepts new measurements only if the joints displacement between 3D mesh models are reasonable given the time between detections. Here we show the results of the human tracking module, with in blue the pose graph edges and in red the detected human. Clearly, building a 3D mesh with dynamic elements may introduce artifacts that we must address. In our case, dynamic objects both affect the localization and the mapping modules. Therefore, we use an inertial-aided Lucas Canada tracker, which discards feature tracks that do not follow the expected per-frame rotational optical flow inferred from the gyroscope, and a 2-point ransack that also uses the ionic rotation to prune outlier correspondences in the feature tracks. On the mapping side, we are able to avoid integrating depth measurements from dynamic elements by discarding those measurements that correspond to pixels from dynamic objects in the 2D semantic image. Then, in layer 3, we encode places and the structure of the 3D scene. First, we define as a place a region of the scene that is not occupied and where the robot can navigate. Two places are connected by an edge if we can go from one place to the other in a straight path. Therefore, the constructed graph is a topological map and allows for path planning queries. We use the work of Olejnikova and colleagues to automatically build the topological graph. We further detect and represent the 3D structure of the scene as a combination of walls, ceiling, and floor, as can be seen in the left figure. Then in layer 4, we construct the room layout of the scene. We encode rooms with a 3D pose, a bounding box, and a semantic label. Connectivity in the graph represents traversability from one room to the other, meaning there is a door connecting both. We do not need to explicitly detect doors, since the topological graph provides us with sufficient information to infer the way rooms can be traversed. All elements in layer 3 have an edge to nodes in layer 4 if they are in the corresponding room. Detecting rooms remains a challenging problem in a general setting. Nevertheless, in our context, we found that a simple technique achieves near perfect results. In our approach, we make use of the Euclidean sign and distance function, also known as ESDF, which encodes for each 3D point in space the Euclidean distance to the nearest obstacle in the scene. Our insight is that the 2D ESDF is constant almost everywhere in a 2D slice near the ceiling, as can be seen in figure A, where all the values are encoding the distance to the ceiling except when we get close to a wall where the ESDF decreases to 0, meaning it intersects with the wall. Figure B shows that truncating the ESDF gives us a good signal of the room layout. Then, as can be seen in the top right figure, we add a label to each 3D place falling inside an ESDF room, and then use the topology of the layer 3 to propagate the labels to nearby nodes. It then becomes also trivial to connect rooms together and infer the door positions by just looking at which edges connect places in different rooms. Finally, we abstract the 3D scene graph using building nodes. In our case, we have a single building node that encompasses all room nodes. Finally, we have our hierarchical 3D scene graph with meaningful connections between different layers that can be exploited for a myriad of applications, as we detail in our paper. In this talk, I would like to quickly present a semantic path planning query. Here we show a small drone that is requested to reach another room in the scene. The path planning can be done at multiple levels of abstraction, starting from the room layout, then the topological map, and finally the ESDF layer. This approach speeds up path planning queries and allows for semantically meaningful requests. Thank you very much.
Yeah, thank you. I think that's all for our morning session. And if you have any questions, feel free to chat in the chat room because the whole Zoom is open for the full day. And our afternoon session will start on 2 p.m. Pacific Daylight Time at Seattle time. And we'll then have few invited speakers and also a few more invited talks. Yeah. See you guys this afternoon. Yeah. And have a good break.